Hello everyone, this is a data structure class, chapter 4. Okay, so we are going to study 4.7 sections about sparse matrix. Okay, we are very familiar with what is a sparse matrix. Okay, sparse matrix means that there is not so many non-zero values. So almost most of the zero values are filled with this sparse matrix. So we have seen how we can represent this sparse matrix in array in chapter 3. But this chapter 4, we can represent this sparse matrix as a circularly linked list with a header node. Okay, so we can represent non-zero value node as a non-zero value element in sparse matrix as one node in linked list. Okay, so that is a very intuitive representation of a sparse matrix. If we are very familiar with linked list, it is very intuitive. Okay, so it's a very similar representation for each row of a sparse matrix. Yes, it's I think it's very intuitive. And each node has a tag field. Tag. Do you understand what is a tag? Tag means that it is called flag field. Flag. That is used to distinguish between header node and the entry node. So tag header means that it is a header node. Tag entry means that it is element node in the linked list. Okay, so and also each header node has a 3 additional field in addition to this tag field: down, right, and the next. Down, right, and the next. So all of these 3 additional field is one of a link field. Link, it's a point to link next or the other node of address, node's address. Okay, and header node for each row I, also header node for column I. Okay, it's very confusing, but I can explain it in the next slide. So there is a one node for row I, and also at the same time, this node will be used for column I. Okay, because they include both of row link and column link. This is a row link, and this is a column link. Okay, so we can say that header node for row I is also the header node for column I. Yes, the total number of header node is the maximum number of row and the maximum number of columns. Yes, if we have a 4 by 4, 4 by 5 matrix, then the total number of header node is maximum of number of row and the number of columns. Yes, 5 is maximum values. So the necessary total number of header node is 5. Okay, so it's very important to understand these sections. Okay, that's all. And let me go. Next one. And that was a header node. And the next one is entry node. Element node has 6 fields. Okay, it also has a tag, row, column. This is a location of non-zero values, and the down, right, and the value. So the value means that non-zero values. Okay, so and this down and right means that link field. Link field means that it is pointer values to pointing next non-zero terms in the same columns down. And the right means that it is a next non-zero term in the same row. In the same row. Okay, so number of row by times number of column matrix with a number of terms, non-zero terms needs a maximum number of row, number of columns plus number of terms plus one node. Okay, yes, it's this is for header node. This is for entry node. And plus one means that header node over header node. Yes, this is for header node of header node. Yes, so that's for only additional one node is necessary to represent a sparse matrix in linked list. Okay, so that means that the total storage will be less than number of rows by number of columns when number of terms is sufficiently small. Okay, so this is a determinant of the time complexity in this representation method. Okay, it's very good. And now this explains the previous slide in figures. So header node has, this is one node for header node, has one field, 1, 2, 3, 4 field. Okay, and this next means that it is next header node. Next header node, and the down field means that it is a 4 column. Right link field means that it is a 4 row. Okay, so one header node include both column link field and the row link field. Okay, so we need only maximum of number of column and number of rows, because each header node include both column link and row link. Okay, that's about the header node. And what is element node? Element node means that non-zero value node. Okay, so non-zero value node has 1, 2, 3, 4, 5, 6 node. 6 field are used for element node. Tag field means each will have a value entry, and the row and column means that the location of a non-zero value. This value means non-zero value, and the down means that it is the next non-zero value in the same columns, and the right link field means that the next non-zero value in the same rows. Okay, so this is an example of element node AI. So AI is a non-zero value, and the location of this non-zero value is I row and j columns. So the value of the tag field is entry, it's a text, and down means that it's one of a link field to pointing next non-zero values in the same columns. And right means that it is the next non-zero value of the same row. Okay, and this is a header node, but we need additional one header node for header node of the list of header node. Yes, so it will have only it is the same as header node, but uh, it includes no, it is not the same as this one. This is the same as this one element, the same structure of element node, even though it is a header node. This also has tag is entry, not head. It is a header node, but the tag field value is entry. It's entry, the same. And the row field is not the location. It is the number of row in the sparse matrix, original matrix, and the number of columns of the original sparse matrix. And this includes value, but this is a number of non-zero values in the sparse matrix. Yes, it means that this is a structure of sparse matrix. Okay, so and also the down field has null values because there is nothing to point, but right field means that the first header node. This will point to the header node. This header node. Okay, the first header node in the representation. Okay, so the example of D is here, means that this value is entry tag field, and the row number of row is 5, number of column is 4, and non-zero value is 6 among the 20 values, and the down field is null, and the right field will point to the next header node. Okay, so we already knows that number of header node is a maximum number of column and the number of rows. Okay. Okay, this is an example of this representation. This is a 5 by 4 sparse matrix. So we can represent three types of node. This is a header node of a header node. Okay, this is a +1. And all of this H1, H0, H1, H2, H3, H4 are header node. Okay, so how many header nodes are used here? So 5. The total header node is 5 because in the original sparse matrix has maximum number of row and the column is 5. But you can see this one also, but this is not existing, non-existing. Okay, actually not actually existing. It is virtually existing because this also include this field. This field is represented here. Okay, and this field is represented here. In this way, one header node represents row and columns. Okay, and how about the entry node? Entry node, I will change the color of pen. Okay, so this one is entry node. Entry node 1, 2, 3, 4, 5, and 6. Six entry nodes are here because there is a non-zero value, 6 non-zero values. 1, 2, this one is the first one. 1, 2, 3, 4, 5, 6. Yes, there are 6 non-zero values, so we can represent the 6 entry. This is a tag field, and each entry node has a tag field entry and location. Where is non-zero value exist? This is a 0 by 0. 0 by 0 location. So 0, 0, and the non-zero value is 2. How about the 4 here? Non-zero value. Row is 1, column is 0, and non-zero value is 4. How about the 3? 3 is row value is 1, and the column value is 0, 1, 2, 3. 3, yes. And the non-zero value itself is also 3. How about 8? 8 is located at the 0, 1, 2, 3 at the row, and the 0, 3, 0 location, and the non-zero value itself is 8. And 1 here is 3, and the 3 location, 3, 3 location, and non-zero value is 1. And this one is 4, 2, non-zero value is 6. Okay, and then this header node's link field. Link field means that okay, I will change the color of the pen using this one. Link field of this one is down. Down is used for next non-zero value in the entry. Yes, this memory address will be stored in this point value, link field. And also, this is also down. Will point to the next non-zero values. And also, this one will point to the next non-zero values. Okay? Yes. And also the other values, this one will point to the next one. This one will point to the next non-zero values in the same columns. And how about right field? Okay, I will change it another color of a pen. Okay, this one will point to the right field. Okay, so this right field will actually this one, but this one is virtual, so actually this will value with this value will point to this one. Okay, this pointing does not exist. It's a dotted line, but this one actually means that this solid line. Okay, first one. And how about this one? Yes, this H1 right field will point to this one. This node's first address, this address, will be stored in this one. Okay, this link field. And how about this one? This one has no values at the same rows, so nothing, null. This one value will be null. And how about this one? H3. H3 will point to this one. Okay, this one will be dotted line. Actually, this value will store the address of this node. Okay, and how about this one? This value also has, this is a virtual. lines. Actual line is this will point to this one. Starting address of this node. Okay, that's all. That's all. And all of the last line has a circular linked list. So instead of they used null value, they will point to itself. Oh, okay. In that sense, I think this value becomes point to itself. Okay, instead of a null. Okay, I'm sorry. Null is wrong here because all of the node here is a circular linked list. It will go back to the to itself when there is nothing to link. Okay, this is a good explanation about this method. Okay, you must understand completely about this. Oh, okay, I must explain one more things here about the header node. In this header node, the structure itself is entry entry node. So it tag field's value is entry, and this 5 means that number of rows in the sparse matrix. Yes, this is 5 and 4. 5 and 4 is a structure of the original sparse matrix, and the 6 non-zero values number 6 is here, and this is a null. And the right field, it means that the first node of header field, header node. The first node of header node. Okay, so this will point here. Okay, that's all about this one. Let me go next. This is another example, so you can solve yourself here. This is 4 by 4 values. Oh, that's wrong here. That's wrong. This is a 4 by 4 sparse matrix. So this must be 4, not 5. Okay, I'm sorry. And how about non-zero values? 1, 2, 3, 4. Yes, 4 non-zero values. So 6 is wrong here. 4. I'm sorry. And there is 1, 2, 3, 4 non-zero entry node here, and there are 4, 1, 2, 3, 4 header node, because maximum number of 4 by 4 is 4, and additional one node is header node of a header node. This is a 1, this is a 4, this is a 4. Okay, so the total necessary node number is 9. 4 plus 4 plus additional 1 equals 9. Nodes are necessary for these representations. Okay, yes. So this is an implementation of data structure of these representations. So this has a structure, header node, and element node. So element node has entry tag field and entry node. Where is the entry node? Entry node has a value of I and j and aij is entry node, and down right, and header node. Header node means the tag field is a header, and next down right. Okay, is that all? So you must see what is entry node structures. Do you remember what is entry node structure? entry node is that int I, int j, and int aij. Okay, so it's for the location of a non-zero value and the non-zero value itself. Okay, you can see this definition in the previous implementation of this value. So you can look at the textbook or search this one in the slide also. Okay, that's all for sparse matrix. And the last section of chapter 4 is 4.8, doubly linked list. Doubly linked list. Okay, the previous one was the singly linked list. So singly linked list means that there is only one link field in the node. So doubly linked field linked list means that it has two link field in the node. So using this doubly linked list, we can move in two directions. So singly linked list, we can move only one directions. But doubly linked list provide moving left and right directions. So doubly linked list has at least three fields. To point to the left link field, it is called L link, and the data field is item, and the right link field is R link. Okay, so the node of a doubly linked list has three fields at least. Of course, this element item may have many attributes, just like a student is possible. Many attributes are possible in this element item field, just like a student data. So all of the data we want to store will be defined in this element item field. Okay, how we can handle this doubly linked list? Okay, so doubly linked circular linked list with a header node. So if we have one header node for this whole doubly linked list, header node will point. This right link field will point to the first element. This is the first, and this is the last node. Okay, and this left link field of header node will point to the last node. And if we follow the blue line, then it is this one, and this one, and this one, and return to header node. This is forward directions. And if we follow red line from the last, and this one, and going back to header node. This is a backward directions. So if we use doubly linked list, then we can go forward to traverse all of the node in the linked list, and also we can go to backward directions by following to the left link field. Okay, so this doubly linked list will provide both directions. Both directions. Both direction we can move. Okay, backward and forward. Okay, that's doubly linked list. And also, very interesting thing in here is that if there is a one pointer here, if I use this is a one pointer here, we can see that if we follow pointers R link, this is a R link, and then this pointers L link means that this one. Okay, so that's the same. Okay, going forward and going backward, it will be the same positions. So this means that this one, and if we go back to the left and going back to the right, also remains the same locations, PTR. Okay, so we can go back and go back and going forward and going back has arrives the same location PTR. So we can use this characteristic here. Okay, next one is that how we can insert new node in the doubly linked list. Okay, so this is a header node, and this is a new node. This is a header node. If then we will, this is a header node. And then the next right link field will point to the new node, this one. And there is only one node here. That means that the left link field of a header node pointing to the last node. This is a first, and this is a last. Okay, so this one will point to the last node, but this is the same address. And also the left link field will point to the header node. This is a header node. And this will point to the header node also, because this is only one node in this link field. Okay, and then this is a general insertion into doubly linked list. Previous one is that insert first node into the header node, but this is a general insertion into the doubly linked list. So there is one node here, and there is another node, new node. This is an existing node. In here, the address is a node, and I want to insert a new node here. So how can we adjust? Okay, how can we adjust the link field in this insertions? Okay, after this node, I want to insert a new node here. Then how can you adjust link field? So you must adjust the link field of a new node. So new node L link, new node's L link, this one must be this new node. Yes, previous node of a new node is a node. And what is R link of a new node? R link must be the next node of next R link of this node. Okay, so this must be point this one. This is a node's R link. Okay, and then we must adjust this node. So I do not know the address of this dotted node, but we already know that this is a node's R link. Node's R link means that this point. And this pointer's L link is here, this one. This one is a 3. And this one was 2. This one was 1 in the step here. And this node must be changed to this node because the previous of a dotted node becomes new node now. So this, instead of pointing this one, this left link field will point to this one. This becomes 3. Okay, so node's R link, L link becomes a new node. New node is here. New node's address. Actually, it is a starting address of a new node. And how about this one? How about this one? This one, yes, 4. This one was originally the next node of a node was a dotted node, but now the next node of a node is a new node. So this becomes this one. Okay, so this was removed and this one. So that was a node's R link becomes a new node. Yes, so all of the connection between this one was deleted now. Change color. All of the connection between node and the dotted line are removed here. New nodes connections are generated. This one, no. This one and this one. Okay, so that was explained here. Okay, and now I want to ask you, can you change the order of this assignment? Can you change it? No, you must keep the order of this assignment. Okay, so if you change 1 and 3, then new node becomes lost. So you must keep the sequence. First one, second one, third one, and fourth one here. You cannot make new node or any node as orphanage or garbage, orphan or garbage. You cannot make any node as orphan or garbage. So that means the orphan or garbage means that there is no way to access that node in the linked list. Okay, so in order to prevent orphan node or garbage node, you must keep these orders, this sequence in the insertion operation of doubly linked list. It's very important. Okay, so you must understand why you cannot exchange the sequence of the assignment. Okay, you can find if you exchange the sequence, you can find some nodes becomes open node or garbage node. Okay, very important and interesting things here. Okay, so this is a header node and this is a node. This is a node and this is a header new node. So if we want to insert this node, this is a 1 and 2 and 3 and 4. So all of this link becomes removed. Okay, now we can follow this one, next one, and what is the next one? This one. What is the next one? And this one. And what is the next one? This one. Okay, now we inserted a new node into this linked list. This is insertion operations. Okay, and how about delete? How about delete? I want to delete one node from the doubly linked list. Also, we must be careful the adjustment of a link field if we delete one node. So, so there is this one, and this one. This one is not showing here. So I want, this is a node, this is a node, and this is a deleted node. Okay, so there is a left and the right. There is a left and the right link field. So I want to delete this node. How can you do it? I want to adjust the right field of nodes to the dotted node. So deleted L-link and R-link. Yes, deleted L-link and R-link is this one. Okay, this one becomes deleted R-link, this one. This is the first one. First one. And what is this field? This field. Okay, so this field are changed to this one. And how about this one? This one becomes this one. So how can you do it? Deleted R-link, deleted R-link, L-link, yes, this one, becomes deleted L-link, this one, yes, so this one is 2. So this is deleted and this is deleted. Then this becomes opened, open. This become open. So that means this becomes garbage. This becomes garbage. Garbage means that there is no way to access this memory address. Can you access this one? When you delete this one and delete this one, only the inward pointers are deleted. So that means that there is no way to access this memory address. Okay, this becomes open or garbage. So we must return this memory address to the operating system using these free operations. Okay, yes, it's a simple. Now this shows that this is a node. This is a deleted. Okay, so original this deleted L link and R link becomes this one. So this is the first assignment, and deleted R link L link, this one becomes deleted L link, second one. Okay, so that's the same figure of the previous slide. Okay, that's all about delete operation. And that's all about doubly linked list. Okay, so this doubly linked list is most general linked list. Okay, so this is a very important data structure, and also our homework is that only singly linked list. But I want to give another one more homework. Implement the student data in doubly linked list. That is next homework. Okay, so you must implement this doubly linked list in your homework. Okay, thank you. That's all for the chapter 4. We finished chapter 4 now. Okay, thank you.